Hello, everybody. My name is Parkinson, and today I'm going to be demystifying dependency injections. I'm going to be hopefully getting rid of some of the magic and mysticism that might be surrounding exactly what is happening when you're using dependency injection containers in your production code, or if you're not using them at the moment, to show you exactly how they work. And maybe slightly foolishly, I thought it would be a good idea to start this off with a software engineer's worst nightmare, which is audience participation. So, with a show of hands, how many of you have been in that position before where you've spent more time writing the source dependencies or the test data for a test than you actually have spent writing logic for the test or the test itself? I've definitely been in that position myself, and yeah, that pain is not very nice. Two more questions. How many of you use dependency injection in your production code or in your personal projects? Yeah, a few people. And keeping your hands up for me, how many of you actually know how that's working under the hood? Yeah, exactly. It's such a strange thing when you first see it for the first time. I know when I did my first internship, and they were using Spring in Java, and I asked the senior engineer, "Oh, what's this weird bean thing that I'm seeing in the code base? What does this mean? What is it doing?" And they responded with, "Oh, it's just magic. Just copy what everyone else did. It's a pattern. It does some stuff. You don't have to worry about it too much." But I'm really hoping that by the end of this talk, you won't be in that position. You'll be able to know exactly what problems it's solving, what it's doing for you on a day-to-day, and by actually writing a live, working container with you, I will hopefully show you how that works line by line, and also show some drawbacks on using dependency injection that you might want to be aware of when going forth from this. Because dependency injection really is quite a powerful weapon to wield. But in order to need that powerful weapon, there are dragons that we want to slay. And in this case, those dragons are tight coupling and boilerplate code, the kind of two things that all devs fear. And to kind of show you what that looks like in practice, I'm going to switch over some code and show you. So, for the purpose of this talk, I am going to be relying on this reasonably simple test case here, which is you can imagine it as being like a very, very simple sales processing piece of software. This sales software takes in a list of sales objects, which has some customer information, some product information, and then within it has a process sales method, which itself calls a product database and a sales database. Before we fully get going here, everyone can see the screen fine and see all the code fine, right? Awesome. So obviously here, we are very kind of naively instantiating all of the dependencies within the constructor itself. And there are several reasons why this is not great. I'm sure you're reasonably aware of this. Most of it comes down to we want different behavior in different scenarios. For example, if we're testing, or we might want to provide a test version of that service, or we might want to provide a mock, for example. Or we might want some polymorphic behavior there, where in one location we want to handle AWS versus Azure. And so we want a bit more flexibility than what this is offering. And the pattern that we use to kind of solve that is simply just to initialize those fields from the constructor instead. This is essentially what we would call inversion of control. The kind of the person who is kind of determining what instance is being used is not the service itself, it's the caller. And so you're kind of decoupling a lot of that dependency now by having it instantiated in the parameters. Obviously, this now means that we've got to change our main method rather than simply calling it without any parameters. We're going to have to pass those in now. But in this case, it's great, and that's reasonably sensible for this scale of code. But obviously, as our product grows, and as we get more customers, for example, if this was a real production database and production system, and as you get more devs, and as you get more and more and more products building on top of that, that can quickly get out of control. And you can imagine the number of constructors you've got in that list is going to balloon out of proportion. For context, here is one solution out of over 100 that we have at GearSet. Our code base is really quite large at this point. And you can see just how interconnected all of those dependencies are and how many of them rely on each other. And so you can imagine just passing in constructors all the way through the call stack, or having to say, oh, I want a new dependency here, is going to be really, really painful, because you're going to have to pass that through every single class in the call stack. And so you lose robustness in the code, because adding the dependency, it becomes really, really challenging to actually maintain the code base and to grow it at the speed you might want to grow it. And that is especially important at GearSet, because we're a SaaS company with over 300 employees, and we've got, as you can see, a ton of different products, which we want to all work together. We want them to be dependent on each other in the back end, because we want to maximize the value for our customers. And obviously, as a DevOps platform, we really care about not only external DevOps for our customers, but also internal DevOps and DevX as well. So we have found ways in which we are able to eliminate a lot of that pain for our users, and by kind of handling dependencies in a slightly different way. If we're slaying dragons, what we essentially would like is an armory. We want a single place where we know we can go, and we can have all of our swords that we're going into battle with in one place. We've got the tools for each of the different things we're trying to tackle, and that location will handle, in the case of services, the life cycle of a service, the number of instances of that service, what implementation will be used for an abstract type or an interface type, and we want to be able to dynamically create these as and when they're needed, so that we can create whatever service is required in whatever area of the code we're working on, or whatever area of the code the user wants to run. Now, this is where dependency injection comes in. What these frameworks are essentially doing is doing even more inversion of control. A simple example there, we've had the constructor and we pass the dependencies directly in. It's that, but 10 times more, because we're using an entirely separate external class to handle all the lifecycle management, all of the various different kind of instantiations are all being completely decoupled from our main production code. And with that comes a much more flexible architectural design, which is able to adapt and be really agile in the same way that most companies today are agile as well. Now, this all sounds fantastic, but you may be thinking, this sounds a little bit complex. Is it really that simple to reason about? Is it what is actually happening behind the scenes here? And luckily, we can actually create a... Sorry, apologies, one sec. Sorry about the banging noise, by the way. Yeah, we can create a really basic dependency injection container on the fly in just a few minutes. And I'm going to be doing that for you today in C#. Obviously, you can use any language, but I feel like C# is a good example here to be reasonably close to pseudocode. So let's look at the interface we might want to create here. As you can see, we've got some container tests that we've written ready to go. And as you might imagine, these don't work yet because we're not doing anything yet. Our container is very much non-functional right now. But importantly, there are two key methods we want to implement here. The first of these is resolve. I want to be able to pass in any type that I need here, in this case, a sales database, and say, give me one of those instances, please. And I don't want to have to think about what constructor that's using, what dependencies it needs for that. The container itself should have that context and be able to do that for us. And secondly, we have the register method. We want to be able to say, oh, yes, our constructor has this interface type, But every time you see that interface, please give us this specific concrete equivalent. And obviously, we want to make sure that the interface type is implemented by the concrete type we provide. Why are we using this specific interface in this case? Well, the simple answer is it mimics real-world frameworks. So on the left here, we've got AutoFAC, which is the dependency injection framework that we use at Gearset for service dependencies. And as you can see, it's got a register type method and a resolve type, and that syntax is very, very similar to what I'm going to be writing today. But this will depend a lot on the framework, and there are obviously advantages and disadvantages to each. C#, for example, has its own built-in dependency injection library called Host Application Builder, which means you can start off with this without any external libraries. And similarly, other languages like Java have, for example, Spring here, which has a slightly different approach, where you have to define what the constructor looks like and what the parameters look like manually, and then that is then read by Spring along with some reflection logic in order to actually call the right constructors and create those instances on the go. Let's go back to the code and start implementing. So the first thing here is that we want to be able to map a interface type to a concrete version that we know we are able to instantiate. Now, this is very simple, actually. It's just a mapping from one type to another type. We're using a C# dictionary, which is like a Java map, or you may have seen it in map in whatever language you use, but we're essentially just going to store that interface type in our registrations list here. So we're going to get the type of the generic that we are passing in here, and we are going to store that with a map to the concrete type we want. And we can then use that later on. As for the resolve method, what we basically want to do here is we want to be able to look at the constructor of whatever type we want to create, and we want to be able to resolve its dependencies, and then recursively build our way up from very, very basic services to a lot more complex ones. And so we need a way to recurse. I'm going to use this protected method here, resolve, to do this. And so I'm just going to write a very simple wrapper around that. It just makes getting the type slightly more obvious and reduce the amount of pain to do that. The other thing we want to be able to do is now, actually, can we deal with this type yet? Do we have the information we need? And again, there's the two cases in order to figure that one out. If the registrations list has the type that we've been passed in, then there is obviously a concrete value that's corresponding to that the user has suggested that we should use. And so we should use that type. And we're using C#'s outvars here to essentially allow us to have a Boolean value predicate, which also gives us a return value in the case where we can implement the type and that value is true. And so we will return that value here along with a true. The other case is that we've already got a concrete service that we can just instantiate directly. We can just call the constructor or a constructor on that type. And the way we are determining whether or not it is concrete is by using C#'s reflection. On a type object itself, we have fields like is class, is abstract, is interface. And quite simply, if it is a class that isn't abstract and isn't an interface, congratulations, we know we can definitely instantiate this. And so we are similarly going to return that type directly. We don't need to do any mapping in this case, and we can return true. Otherwise, we know this is not something we can deal with yet. We don't have enough information, and so we return false and null. Moving on to the resolve method itself. The first step here is to use this can implement type here in order to determine are we able to handle this or not. So first step is, can we implement the type? If not, we should probably throw some kind of exception that allows the user to know what's happened. And in this case, you could use any exception you'd like. I'm just going to use invalid operation exception because it makes things nice and easy. if we have a value out here, we know that this is a type we can now deal with, or the user has said that we can deal with it, in the case of it being in the registrations list. We now need to get the constructor for that implementation type. So we're going to call, sorry, 1 second. We are going to call getConstructors, which gives us a list of every constructor on that type. And we're just going to get the first of those. You could also use the array index, but in this case, I think first is slightly clearer. We now have a constructor we know we're able to use, and so we want to be able to deal with each of its parameters and recursively resolve each of those. And so we simply use C#'s reflection libraries to get parameters from the constructor, to select each of those values, those types, and resolve them recursively. And then once we know that we've got concrete implementations of each of these, or concrete instances, we can now convert that to array and use that in our constructor. Because we know that this constructor has these parameters, and we know this constructor exists from the type, we can simply invoke that, and we are pretty much done. So if we go to the tests, we can now see that running these results in everything passing. We're able to successfully resolve any types that we pass to it, whether or not they're abstract, interfaces, or concrete, and we're able to register those abstract types so that we have concrete equivalents that we can use. And that then means that we can also use these in tests, in this case, or we can use them in a main method. Now, before we had this sales database product database passing in values here, this will change slightly with a dependency injection framework, because we will now instead be instantiating a container. And in this case, I have this container registration service that very simply is just one method that instantiates and registers every single interface type that we would want to have concrete equivalents for. That container is simply just then returned, and then all we have to do is call .resolve on each of the maybe 3 or 4 different classes you might need for a main method. Not a humongous amount, and significantly less than passing in every single dependency for each of the things you need, and so on and so forth. And so as a result, we're able to get rid of a lot of that boilerplate and a lot of that pain, and we've got something that's a lot more robust. However, you may have noticed there's still a lot of boilerplate here. In this main method, we've got a lot of boilerplate to just create a single sale, just to ensure that, yeah, we can run this main method and we're able to process the sales correctly, and in our test as well. Especially as they get more and more complex, or you might want to handle multiple values. We've got so much boilerplate here to create a product with all of these product names and features and costs, customers with IDs and first names, or sales with mappings from products to specific quantities of that product. It's a lot of boilerplate, and in this test, we don't really care about anything other than the fact that the quantities are less than 3, which for this case, we're simply saying that if the number of objects, the number of a product that a user wants is greater than 3, it's not, they're out of stock, we're unable to do it. It's just a good metric for us to use, but we've got to do all of this boilerplate to get there. That feels really strange, and given we've just used a load of reflection to get rid of that boilerplate, it feels like maybe we can do the same thing here. So, I guess maybe some of you might be a little bit skeptical of this, because there are obvious differences, which I'm going to get to in a second, but there are clear benefits as well to doing that, because you're getting rid of that boilerplate. You're making your tests a lot easier potentially to read, because you're not creating all of those subtypes directly, especially for the fields you don't care about. And on top of that, you're making your tests a lot more robust and resilient by using some kind of injection framework, because, again, it's able to populate any fields you don't actually care about the values for, simply using that recursion, and you can just specifically set the values you want. But there are 2 key differences here between the service container that I wrote on the screen and a test container, this mythical test container that would be able to create test data. First one of these is, in the service example, we have empty constructors, which are like our base case. If you think about it like a induction kind of thing, we've got empty constructors that we always know exist, and we're able to build up from there. Or we're able to kind of bootstrap it with a single service that we're maybe able to instantiate ourselves, let's say. But for test data, we need to generate primitives manually. We need to kind of have methods for each primitive type we might want to create here. And that's going to be a load of boilerplate that is going to be a little bit harder to deal with. And the other one is, again, test data is not services. We want specific values that change between tests. We want to be able to test that if the quantity is greater than 3, things fail, or if the user has a certain name, they're banned because they're in the banned list, and so we don't want to serve them, for example. There's lots of different cases and lots of different fields. We might have specific values, and many others we don't care about for that test. And so we need some degree of customizability there, which is harder to reason about. But we can get around a lot of these issues with some C# tricks, as well as by extending that test container we've already written to handle that. Now, unfortunately, it's a little bit too complex to write it all from scratch in this talk, but I have got the code to share with you, and I'm happy to walk through that with you and show what that will look like. Let's go back to the test container and see what the interface might look like. So again, very similar to before, and this will look familiar. We've got 2 methods we want to be able to implement. We've got a create method, which again creates the type we want. And we can pass in any type we may want here, and it's going to recursively create that with primitive data that is randomly generated, and we're guaranteeing uniqueness for each of these values, as we can see in our tests. The second case, the second method we want to provide is a freeze method, and that's really handy because some of our services might have methods that call return a value of type T, and I just want to be able to say, okay, always give me this specific value when you request that type. And so having a freeze method like this is really handy for those cases. And that slightly differs from the register method we had before because we're dealing with instances rather than types. Now, why is the nomenclature changed here again? We've gone from resolve and register to create and freeze. Again, I'm just trying to mimic real-world frameworks here. So on the left, we've got AutoFixture, which is, again, what we use at Gearset. And again, it has create methods and freeze methods, exactly the same as what we're trying to implement here. But it isn't the only framework for C#. It's not the only framework. There are other alternatives available for most of the major programming languages. For example, Java here, we have a thing called instantiate, which has very similar methods with the ability to be able to create particular object types, and also has some nice utility methods, as does AutoFixture for list, set, map, and also builder methods for ignoring fields that you don't actually care about, for example. Awesome. Now let's go back to the code and talk through what this test container is doing on top of what we already wrote for the service container. We're actually extending it here. So all of the logic we already saw is applicable here. And if we go to our resolve method, ignoring the rest of this code for now, we can see that for interfaces, abstract classes, records, concrete classes, we can simply use that container we've already written to handle those. But there are other types that we will need to deal with here, and other kind of cases we will want to handle differently. And the first of these is freeze. Freeze, again, is allowing us to return a specific instance for a specific type. And so rather than mapping from type, as we did in our other container, we are mapping from type to an object. And so that is what we're doing here. As for the create method, we're simply, again, having this recursive call, which is having to handle both the freezes, which are being fetched directly from that mock instances dictionary we referenced earlier, but also has to handle generics and also those primitives that I mentioned earlier. Let's start with primitives. In the case of primitives, it is unfortunately as simple as having a big old switch statement of creating each of those values. And in this case, we're really relying on GUID and random in order to provide some of that for us. As you can see, we're able to create GUIDs, strings, spools, cars, all the values which we've seen in the DTOs we're dealing with here. As for generic values, we have the ability to use reflection again, to use generic type definition to get what that type looks like, and to check what type of generic type definition it is. So we've got nullables here, which we're returning simply the non-nullable equivalent of that. And we've also got collections like lists and dictionaries, where we are digging slightly further in, checking the number of arguments, checking we have a valid list or dictionary method, and for each of those, if we have a valid type, we are simply creating an empty list or dictionary and using the resolve method again recursively to populate that list with some number of values. And same for the dictionary/map for the key value. As a result of that, we end up with a fully featured resolve method that is able to handle every single type we might want to use for tests. And what we're gaining out of that, we're getting a really, really nice benefit here, which is simply how much code we're able to remove from a test. So here was that previous test I showed you before. We've got 10 lines of code to create a list, and that simply gets reduced down to create many of count 2. That is obviously way simpler and is a lot easier to read as an end user and maintain. Now, obviously, I can wax lyrical as much as I'd like about dependency injection, but there are some downsides that I think are worth considering. And a lot of these have just come down to the fact that there is an element of indirection there. From where your dependencies are defined. You've got that contained in instantiation service that I mentioned earlier. All of the like lifecycle management and everything is in that location rather than where you're defining your classes. And so there is some context needed there to be aware of what's happening and to be able to maintain that as things go. And so, for example, if you come across memory issues or you come across a circular dependency issue, which is where you have interfaces, services that reference each other and depend on each other, a lot of those pain points are going to hit you not in compile time, but in runtime, because that's where your objects are being created for most frameworks. It is worth noting that that's not the case for all of them. There's Dagger, for example, for Java, and other equivalents for other languages that do some of this dependency injection at runtime, compile time. And so you get slightly earlier on in the process those same kind of alerts. And it's also worth noting that even for the runtime light frameworks like what we use, AutoFixture, it's providing lots of nice utility methods and lots of nice error handling as well to make that whole process really nice and seamless to use, where I think personally the benefits outweigh the disadvantages. So you can see here, for example, being able to have lifecycle management by allowing singletons, which are used everywhere, or having decorators, for example, if you wanted to have a logging decorator to do some observability services and handling that for every single type with one line of code, or having using a specific constructor to instantiate the concrete types you might want to create. The other key points here is that it can lead to some bad habits kind of happening, because at the end of the day, you have that indirection, and you're not going to feel nearly as much pain anymore with having a constructor that's 20 parameters large. You can start to lead into some kind of bad architectural decisions, and so you've got to be really, really cognizant of that when designing your code, because there are obviously other benefits to designing your code well. But I think most importantly, the concept of dependency injection is quite confusing, especially for new devs. And so it's really important to be aware of how it works and to really share this knowledge with people at your company. And so I really hope this talk has been able to kind of give you slightly more context into the magic behind dependency injections and to slay those dragons that you might have if you don't use them already. I've left a QR code in the top corner, which is a link to the GitHub repo I've used for the code I've used today, which I would love if you were wanting to use to share, this same information with your colleagues. If you'd like to ask me any questions, I can either do so now, or I will be at the GearSet booth in a yellow polo with my purple hair, so hopefully I'm not too hard to spot. Thank you very much for listening to my talk. I've been Jack Parkinson, and I hope you have a great rest of your NIDC.
Thank you, Jack. I think we have some questions for you.
Yeah, thanks for the talk. So, having worked on some big monolithic applications that used AI, one of the issues I found is when you go to do a system test, so you're testing how different components interact, you end up just bootstrapping the entire DI container and just mocking out a few services, and that becomes your test fixture. Problem is it's so slow. When you have 1,000 or 2,000 of these tests, it's taking 40, 50, 60 minutes to do a full run. I'm just wondering if you have any insights on,
I mean, first of all, it will depend very much framework. As I mentioned, there are some frameworks that are designed more for performance concerns, like Dagger, where it's using compile time rather than runtime to a lot of that. That's going to have drawbacks in terms of how much setup there is required, how much kind of manual kind of boilerplate you're going to have to write maybe to do that at that stage of the build process. But I guess the other point is a lot of these frameworks will have specific, the ability to use a different kind of instance of a container for for different runs. So you'll have a test container for your test, and you'll have a regular container for your regular test, and you'll use those instances in different locations. If you look through the documentation, some frameworks will have the ability to kind of give you some insight into where that kind of pain is. And it may also be you may be able to look into singletons, for example, rather than having different instances for every single service. You can use a singleton everywhere if it doesn't matter too much about sharing code. If you've got a static, for example, and that might help reduce the number of steps and operations it's doing. And so that build time will hopefully greatly decrease there.
Yeah, cheers. Thanks.
Thank you, Jack.
Awesome. Is there any other questions from anyone? Yeah. Thank you very much, everyone.